Okay, so let's now do the energy balance with this leaky atmosphere, as we called it, where it's not absorbing all of the long wave energy coming from the surface. It's absorbing a fraction of it and allowing a fraction of it to go through. And its temperature, atmosphere's temperature, is then determined by how much of the long wave it's absorbing. Okay, so what does the energy balance now look like? You have, again, top of the atmosphere, always start there. You have the total shortwave effectively being taken by the system, which is again 1 minus alpha. Atmosphere is emitting at its temperature, Ta, so A is going out, sigma Ta to the fourth, plus the atmosphere is also emitting something directly from the surface that was allowed by the atmosphere to go through, which we called 1 minus epsilon S from the surface. So epsilon is the absorptivity of the atmosphere. I'm using transmittivity and absorptivity as the same because there is a Kirchhoff's law we will see later on, and so on. So what's happening at the surface? Surface is still getting the short wave, and it is getting the downward long wave from the atmosphere. Okay, atmosphere is Ta, sigma Ta to the fourth is coming down to the surface, and that's what determines how much energy the surface has to lose as long wave for its equilibrium. Okay, so you have two equations, fairly straightforward. You do the little manipulation here and look for S going up. You use A, remember this and this are the same, because that depends on the temperature of the atmosphere, its black body radiation. So obviously outgoing long wave from the surface is sigma Ts to the fourth, where Ts is the surface temperature. If you manipulate these equations, you end up with an expression for S. So you add A from here. You get 1 over 2 times 2 minus epsilon times 1 minus alpha p times S0. I will let you do these manipulations. Fairly straightforward stuff, not a big deal. So now the expression for S looks a little bit more complicated. It's got 2 divided by 2 minus epsilon. Okay, so we added the expression for 1 minus alpha S0 in terms of sigma Te to the fourth, or A. They're all the same. A is sigma Ta to the fourth, but Ta is the same as the emission temperature, a simplifying assumption. So Te and Ta are the same, which means A is sigma Te to the fourth. Okay, that's what we did. How do we think about it? So Kirchhoff's law states that emittance of a body, which is the ratio of the actual emitted flux to the flux that would be emitted by a black body at the same temperature, equals its absorptance. Emittance and absorptance are the same, and it's the fraction of the actual emitted flux as opposed to a pure black body which would emit everything, right? A pure black body takes energy, reaches some temperature, and emits all of the energy it received as black body radiation. Okay, so this expression for Ts now looks a bit more complicated, but you can see the similarity to the previous expression already when we allowed the surface long wave to go right through, to be completely absorbed by the atmosphere. Why? Because if you make epsilon equals 1, which means the atmosphere is completely opaque to the surface long wave, then you still get 2 to the 1/4 Te as before. Okay, if this atmosphere is completely transparent, then it would go to 0. Then temperature of the surface would be the same as the emission temperature. Very simple, right? And the atmospheric long wave obviously is sigma Ta to the fourth, but now it's got a factor epsilon because it is not a pure black body anymore. It is absorbing part of the energy and transmitting only part of the energy. So in general, epsilon is between 0 and 1. TE is still less than TS, but this time TS is greater than 2 to the 1/4 if the atmosphere absorbs part of the energy going out, which means atmospheric temperature will get warmer, it'll send more energy down as long wave, and so on. So the details are still the same, that the surface temperature is going to be warmer than the emission temperature if there is a greenhouse effect, or if there's an atmosphere that is not completely transparent to outgoing long wave from the surface. So some of the energy will be absorbed by the atmosphere, and the atmosphere loses energy to space depending on its absorptance or emittance, but it will also send that energy back to the surface based on its absorptance and emittance. Okay, it's fairly straightforward. So this is just the same thing. The outgoing long wave and downgoing long wave are sigma TA to the 4th. This time TE is not the same as TA because we have a fraction here, that is the absorptance. So atmosphere is keeping some of the energy. You can think of it that way. So you add again the energy balance, right? Top of the atmosphere is what's escaping from the surface and what's being emitted by the atmosphere, and what's the energy that is being taken in by the system in shortwave, and you manipulate these equations. So the surface balance is what's coming from the atmosphere plus the shortwave. So this is for the atmosphere, this is for the surface. Don't get confused, just pay attention. And S is still sigma TS to the 4th, and that's the relation we just derived. So atmospheric temperature now, using this relation, okay, this we are putting in the TE here. TE and TA are not the same, right? So TA is now related to TE with this relation, and again, if atmosphere is completely opaque to S, then you will get 1/2 of TE as atmospheric temperature. So epsilon is 0, and or completely transparent, and if it's completely opaque, this becomes 1, so then TA becomes TE. Okay, so atmospheric temperature is now 1/2 to the 1/4 of TS, because it is allowing some of the energy to be lost, right? So it's smaller than the surface temperature by this amount. Again, it's just very, very simple algebraic equations that you can just derive and make sure you understood. Okay, very simple.